Imagine waking up tomorrow morning, right? You pour your coffee, you sit down at your desk, and you open your laptop.
Okay.
And you have all your professional skills perfectly intact. Like, you know how to code, you know how to analyze a spreadsheet, you can craft a compelling email, your grammar is
You're
flawless.
fully capable.
Exactly.
Yeah.
Your logic is totally sharp, but you have absolutely zero memory of what happened yesterday.
Oh, wow.
Yeah, you don't know what projects you're working on. You have no idea what company you even work for. You don't recognize the name of the colleague who literally just messaged you.
Right.
You are essentially this highly capable, incredibly intelligent blank slate. And you're forced to figure out your entire context from scratch every single day.
I mean, it's an exhausting scenario just to visualize. Being frozen in this permanent state of amnesia, despite being armed with a genius-level intellect.
Yeah.
You would spend like 90% of your day just trying to read old emails to understand who you are before you could actually do any meaningful work.
Exactly. And welcome to the deep dive to our resident learner out there listening, because today we are exploring something that affects you every single time you open up a chat window or trigger an autonomous agent or really use any AI tool in your workflow.
It's incredibly relevant to everyone right now.
It really is. Our mission today is to tackle the most critical, yet somehow deeply misunderstood bottleneck in artificial intelligence today. The reality is that even our most powerful, mind-blowing models, the ones writing code and passing bar exams,
Right.
they are essentially trapped in that exact state of permanent amnesia. We are going to explore the mechanics of this amnesia, and more importantly, how the brightest minds in the industry are attempting the literal digital brain surgery required to break them out of it.
And to guide this exploration, we are pulling heavily from some foundational frameworks that have really defined this space lately.
Yeah, some great sources today.
Definitely. Andreessen Horowitz published this massive, really clarifying piece on the mechanics of continual learning. It outlines the architectural boundary the industry is hitting right now.
Which is fascinating.
It is. And alongside that, the tech analysis team at Best Partner broke down these concepts, and they really grounded them in the empirical failures we see in the tech industry today.
Right.
So we are moving past the hype of, trillion parameters and looking at the microscopic mechanics of how a neural network either actually learns or just pretends to learn.
Okay, let's unpack this because I'm so eager to get past the surface level narratives here. We constantly hear that models are learning when we talk to them, right?
We do hear that a lot, yeah.
But to understand why they actually aren't, I want to lean into a cinematic analogy that perfectly frames the architecture of modern AI. We need to talk about Leonard Shelby.
Yes. The protagonist of Christopher Nolan's film Memento. It is arguably the most accurate conceptual mapping for a large language model post-deployment. For anyone out there who hasn't seen it, Leonard suffers from a traumatic brain injury.
Right.
And this injury leaves him with a severe condition called anterograde amnesia, meaning he remembers his entire life up to the exact moment of the injury.
So he has a foundation.
A rock-solid foundation of skills. He can drive a car, he knows how to speak, he can use a firearm, he understands human psychology. But his brain has lost the physical mechanism required to form new memories.
Right. His world just resets every few minutes.
Exactly. He is stranded in a perpetual agonizing present.
And because he knows he has this condition, right, Leonard has to build this desperate system of external scaffolding to survive and solve his mystery.
Right, because his internal synapses won't update.
Exactly. So he offloads his memory into the physical world. He takes Polaroid pictures of people, writing, "Do not trust him" on the back.
Yeah.
He leaves sticky notes on his mirror. And for the most critical, unalterable rules of his existence, he literally tattoos them onto his own body.
It's extreme, but it works for him.
Right. These are external props replacing internal cognition. He can function, he can navigate complex situations, but he never actually internalizes a single new piece of information.
And if we look at the AI models you use every day, well, they are Leonard Shelby.
They really are.
When a major AI lab spends $100 million to train a massive foundation model, they feed it a staggering portion of the internet, right?
Right.
The model processes this. Its neural weights shift and adjust, and it learns the fundamental structures of human language and logic. But the moment that massive training run ends, the model is frozen.
That's the moment of the brain injury.
Precisely. All of that vast knowledge is baked into its parameters. Post-deployment, once it is actually serving your requests, it learns absolutely nothing new internally.
This mapping is almost uncomfortably accurate when you look at how we build AI applications today. I mean, the entire tech industry has essentially spent the last 3 years building a highly sophisticated version of Leonard's tattoos and Polaroids.
That's a great way to put it.
Right, like when you use an AI assistant and it magically remembers what you said 3 prompts ago, it hasn't learned anything. That is just chat history.
Yeah, it's an illusion.
Exactly. The application is secretly taking your previous messages and repasting them invisibly into your new prompt. Those are the short-term sticky notes on Leonard's bathroom mirror.
And then consider the enterprise tools. Let's say a company builds an AI that can answer questions about their proprietary internal HR documents.
Okay.
The model wasn't actually trained on those documents. Instead, it uses a technique called Retrieval Augmented Generation, or RAI.
RAG. Yeah, we hear that term a lot.
Right. So when you ask a question, the system rapidly searches a database, finds the relevant PDF, and pastes the text of that PDF right into the AI's context window before asking it to answer you.
So that's Leonard's stack of Polaroids in his external notebook.
Exactly. The model is looking up facts it does not intrinsically know.
And then we have the system prompts. These are the hidden instructions that developers inject into the context window before you even say hello. Like, you are a helpful assistant. You do not use foul language. You answer in markdown format. Those are the tattoos.
Your tattoos? Yeah.
They are permanent guiding instructions written on the outside to tell the amnesiac who it is supposed to be today.
The overarching term for this entire paradigm of external scaffolding is in-context learning, or ICL. And we really have to ask why it has been so dominant.
Why have we accepted this amnesiac state, Lutz?
Exactly. And the answer lies in the fundamental architecture of the transformer, which is the mathematical engine beneath almost all modern models.
Okay.
At a mathematical level, a transformer is a conditional next token predictor.
So based on my reading of how transformers actually operate, the key word there is conditional, right?
Yes.
The underlying weights of the network are completely static, but as you feed text into its context window, which is its temporary working memory, that specific sequence of words activates different pathways through the static weights. It's like water flowing through a fixed network of pipes, right? Depending on where you pour the water in, it exits from a different spout. You aren't changing the pipes, you're just changing the input condition, which produces incredibly rich, varied behavior. Am I framing that correctly?
That is a highly accurate way to visualize it, actually.
Yeah.
You are manipulating the latent space of the model without altering its physical structure at all.
Okay.
The model's apparent capabilities can change radically simply based on the prompt. This is exactly why prompt engineering became such a massive field.
The real-world proofs of this are just staggering. I mean, take Cursor, the AI coding assistant that has totally taken the developer world by storm.
Oh, Cursor is a perfect example.
It feels like magic. It
Yeah.
feels like it deeply understands your entire code base. But the developers behind it are very open about the fact that the underlying model weights are totally fixed.
Right, they aren't training a new model for you.
No, the magic of Cursor is actually just a masterclass in prompt orchestration.
Yeah.
The system is incredibly smart about knowing which snippets of your code to retrieve, when to summarize an old file, and how to structure the invisible context window so the amnesiac model can seamlessly write the next function.
And we see the exact same phenomenon with autonomous agent frameworks, too.
Like OpenClaw.
Exactly. Look at a project like OpenClaw.
Yeah.
They didn't have access to some secret fluidly learning model.
Yeah.
They used the same static models available to the general public.
Okay, so how did they do it?
OpenClaw succeeded because it elevated the design of the agent harness to an absolute art form.
The harness?
Yeah, it tracks what the AI is doing. It creates a structured temporary memory,
Yeah.
evaluates intermediate steps, and then surgically decides what specific information needs to be re-injected into the prompt for the next step.
Wow.
It is essentially an automated system for managing Leonard Shelby's sticky notes at superhuman speed.
Okay, let me play devil's advocate here because this brings up a glaring question for anyone looking at the success of these tools.
Go for it.
If these external interfaces work so phenomenally well, like if Cursor is actively helping engineers write production code and RAY is successfully powering enterprise search, why are we telling the listener that this paradigm is a dead end?
It's a fair question.
If Leonard Shelby is successfully solving the mystery using his tattoos and Polaroids, aren't these external tools getting the job done? Why do we need the AI to actually learn?
It is the most important question in the field right now. And the simplest way to understand the limitation is to examine your own daily workflow.
Okay.
Think about how you interact with an AI today. You are never actually teaching it a new skill. You are essentially handing it a painstakingly detailed 50-page instruction manual every single time you ask it to perform a task.
Right.
If you want it to format a report a certain way, you have to provide the template, the rules, and the examples in the prompt every single time.
Because the moment I close the window, the manual burns.
Exactly.
The next day, I have to print out the 50 pages and hand them over again.
Precisely. And this is where we hit the hard physical and mathematical limits of in-context learning.
Okay.
It's breaking down because of the immense pressure that modern agentic loops are placing on the context window.
Agentic loops.
Right. We are no longer just asking an AI a simple question like, translate this paragraph. We're deploying them as autonomous agents.
Right. The goal now is to give a high-level command, like, go research this competitor's product line, write a comparative analysis, write a Python script to scrape their pricing page, and compile the results into a slide deck.
Yes, and to execute a complex, multi-step loop like that, the agent needs to constantly pass context from its prior iterations to the next.
It has to remember what it just did.
Exactly. It has to hold its initial instructions, the search results it found in step 1, the code it wrote in step 2, the errors that code generated in step 3, and the revised code in step 4.
And this is where the house of cards collapses, right?
It really does.
Yeah.
The industry data shows exactly where this breaks down. After somewhere between 20 to 100 steps of an autonomous loop, these agents just lose the thread entirely.
Wow, 20 to 100 steps.
Yeah. Their working memory, the context window, fills up with all these intermediate steps and scratchpad notes.
So what happens?
The coherence degrades, and they stop converging on a solution. They basically get buried under their own massive pile of sticky notes and start hallucinating or looping endlessly.
So how is the industry trying to fix this?
Well, the industry's current, arguably brute force approach has been to engineer models with ultra-large context windows.
It's build a bigger desk.
Exactly. If the agent runs out of desk space for its nodes, just build a bigger desk. We've seen context windows jump from 4,000 tokens to 1,000,000 tokens, or even larger.
Wow.
But to do this, researchers had to confront a massive mathematical bottleneck in the traditional transformer architecture.
Let's unpack the math here, because this is where a lot of people get lost in the jargon, I think.
Yeah.
Traditional transformers use something called a KV cache, a key value cache, to maintain the memory of the context window.
Right, correct.
But this mechanism scales terribly. It has an O of n squared computational complexity limit.
Yeah, let's ground that notation in reality. O of n squared means that as the context grows, the computational cost doesn't grow in a straight line. It explodes exponentially.
Okay.
In a standard transformer, the attention mechanism requires every single token, every piece of a word, to calculate its relationship to every other token that came before it.
Wait, so if I feed the model a 10-page document, it does a certain amount of math?
Right.
If I feed it a 20-page document, it doesn't do twice as much math.
No.
It does 4 times as much math.
Exactly.
And if I feed it a 100-page document, the math required is just astronomical.
It is. The memory required to store the KV cache on the physical GPU chips literally hits a hardware wall. It becomes financially and physically impossible to run. That exponential wall is exactly why the industry has been aggressively shifting toward state-space models, or SSMs, and architectures utilizing linear attention.
Right.
These models abandon the traditional KV cache. Instead, they use a fixed-size recurrent state.
So how does that work?
As new text streams in, the model continuously updates this fixed block of mathematical state, basically compressing the history as it goes.
The beauty of that is it achieves O of n scaling, linear scaling.
Yes.
If you double the size of the document, the computational cost only doubles. It makes it mathematically feasible to feed a model a 10 million token context window without, melting down a server farm.
True.
Huh.
But there is a severe architectural trade-off that is rarely discussed in the marketing materials.
What's the catch?
Well, a traditional transformer attention mechanism has what we call lossless recall.
Okay.
Because it calculates the relationship between every single token. If you drop a specific fact into token number 500 and ask about it at token number 100,000, the model remembers it perfectly.
The KV cache is a perfect, lossless record of the prompt.
Exactly. And the state-space models sacrifice that. Because they are constantly updating and compressing incoming information into a fixed-size state matrix, They suffer from lossy recall.
So older information in the prompt gets squeezed or blurred or completely overwritten by newer information.
This is the physical reality of compression.
Yeah.
You are trying to fit an unbounded amount of sequence data into a bounded mathematical box.
Right.
So yes, SSMs allow agents to theoretically survive 20,000 steps without crashing from memory exhaustion, but their working memory becomes slightly blurry.
Okay, wait. Let me push back on this entire trajectory for a second.
Sure.
Whether it's a massive transformer with a giant KV cache or a brilliantly efficient state space model, are we still missing the forest for the trees here?
How so?
Giving an amnesiac a 2 million token context window is just giving Leonard Shelby an infinitely long roll of tattoo skin.
That's exactly right.
We aren't curing the underlying condition, we are just giving him more surface area to write on.
You've isolated the exact philosophical and technical dead end of the current paradigm. And to truly understand why an infinitely large context window does not equal intelligence, we can look at our own digital behaviors.
Yeah, think about your web browser, right?
Exactly.
If you are researching a complex topic and you open 300 tabs, does having those tabs open make you smarter?
Definitely not.
Have you internalized the knowledge of those 300 articles? No. You are just overwhelmed.
Yeah, you haven't learned the information. You just know roughly where it is temporarily located.
And the AI with a massive context window is facing the exact same cognitive overload. It hasn't internalized the structure of the data, it's just juggling it in a temporary buffer.
This leads us directly to a foundational theoretical concept. Ilya Sutskever, one of the primary architects of modern deep learning, frequently uses an analogy about what true intelligence actually requires.
Okay.
He asks us to imagine that we have engineered a super-intelligent 15-year-old.
A prodigy.
A profound prodigy. This teenager has a phenomenal foundation of cognitive skills. They can reason flawlessly, they can read any language, they can do complex mathematics,
Wow.
but they lack specific, deeply held professional knowledge.
Because they're 15.
Right. You can't just take this brilliant teenager, hand them a 2,000-page textbook on neurosurgery, push them into an operating room, and say, okay, the patient is ready, read the book, and perform the surgery.
That would be terrifying.
The absurdity of that scenario is exactly the point. Becoming a master surgeon or an elite software architect requires deployment into the real world.
It requires practice.
It requires a sustained period of trial, error, practice, and critically, a process of learning post-deployment.
Right.
True intelligence isn't just dropping a finished, pre-trained brain into a novel environment. It is the capacity of that brain to physically and chemically change its own neural pathways based on the friction of experience.
This highlights what the Andreessen Horowitz analysis calls the filing cabinet fallacy. And I love this concept.
This is a great framing.
Imagine an enterprise builds the ultimate knowledge retrieval system. Right, it has infinite storage. Every single document, fact, and data point in the history of the universe is perfectly indexed.
Okay.
It can retrieve any specific fact in milliseconds and paste it into a prompt. Has that system learned anything?
The mathematical and philosophical answer is absolutely not.
Right.
It is merely stored data. It has never been forced to undergo the difficult, destructive process of true learning.
Which begs the question, if learning isn't storage, what actually is learning in the context of an artificial neural network?
Learning is lossy compression.
Lossy compression.
This is a vital concept to internalize. During the initial massive pre-training phase of an LLM, the training algorithm takes petabytes of raw, chaotic internet text and forces the model to compress it into a relatively tiny set of parameters, the weights of the neural network.
But they aren't just zipping a file, like creating a .zip folder on your desktop.
No, because a neural network doesn't have the capacity to memorize every single sentence on Wikipedia perfectly.
Right.
To minimize its error rate during training, the network is mathematically forced to extract the underlying structure of the data. It is forced to generalize.
So it's finding patterns.
Exactly. It has to discover the rules of grammar, the structures of logic, the archetypes of human storytelling. Because storing the rules takes up vastly less parameter space than storing the raw text.
So the model that perfectly memorizes the data is actually a failure.
Yes, it's called overfitting.
Overfitting. Okay, so the model that throws away the specific words but keeps the underlying concepts is the one that achieves high intelligence.
Yes.
That lossy compression, the forced extraction of structure, is the learning.
And this brings us to the grand irony of the current AI industry. The exact mechanism that makes these models so incredibly powerful, their ability to compress raw experience into compact structural wisdom.
Yeah.
That is the very mechanism that we completely disable the second the model is deployed to the public.
Wow. We freeze the weights.
We do.
We tell the system, you are no longer allowed to truly learn. From this moment forward, you are only allowed to look things up in your external filing cabinet and hold them in your temporary working memory.
To illustrate why this is a fatal limitation for the future of AI capabilities, we have to look at the outer bounds of human cognition.
Okay.
The literature points to two legendary figures in the history of mathematics to demonstrate the limits of retrieval: Andrew Wiles and Grigori Perelman.
These stories are incredible. Let's look at Andrew Wiles.
Sure.
For over 350 years, Fermat's last theorem stood as the most famous unsolved problem in mathematics, right? The brightest minds across centuries tried and failed to prove it.
Right.
And the reason they failed wasn't because they lacked access to the right library. It wasn't a retrieval problem.
No, it wasn't.
The conceptual distance between the established mathematics of the 17th century and the eventual solution was simply too vast to bridge with existing knowledge.
And Wiles famously worked on the problem in near total isolation for 7 years.
7 years.
To solve it, he couldn't just query a database of old mathematical proofs and rearrange them in his context window.
Right, he had to build something new.
He had to forge a completely novel theoretical bridge between two highly distinct, previously unconnected branches of mathematics: elliptic curves and modular forms.
Wow.
He had to invent entirely new conceptual machinery.
And Grigori Perelman's proof of the Poincare conjecture is the same story, right?
Exactly the same. The leaps of insight required to map out the topological structures he proved did not exist in any text.
You couldn't prompt a model to find it because it hadn't been written down yet.
Right. These breakthroughs required the physical hardware of the human brain to fundamentally update its internal priors.
Yeah.
Wiles and Perelman had to physically alter their neural synapses over years of deep focus to conceptualize architectures that transcended their training data.
Okay, I have to pause here because this raises a massive empirical and philosophical question.
Let's hear it.
We are looking at these towering human achievements, right? Does the isolation and deep neural restructuring of Wiles prove that our current AI paradigm is fundamentally hitting a ceiling?
That's the big debate.
Does it prove that without parametric structural learning, an AI will never have a true eureka moment? Or is it possible that we humans are just romanticizing our own biology?
Oh, it's interesting.
Like, could you argue that even human genius is just a complex recombination of data, and an LLM could eventually prove a 300-year-old theorem if it just had a big enough context window and enough compute cycles to shuffle the sticky notes?
That is the dividing line in AI research today.
Really?
Yeah. One camp believes that scale is all you need.
Ah,
That if you make the context window large enough and the retrieval sophisticated enough, novel intelligence will spontaneously emerge from the recombination.
okay.
The other camp, which is heavily represented in our sources today, argues that without the friction of parametric updates, the physical rewriting of the latent space, a system is fundamentally barred from true synthesis.
So it's still...
It can only ever interpolate between known data points. It can never extrapolate into the unknown.
I want you, the listener, to challenge yourself on this. Think about how you experience a paradigm shift in your own understanding.
Yeah.
When you get that true aha moment, when a chaotic, complex topic finally snaps into sharp focus. It's almost never because you read a single defining sentence.
Well, it's a process.
It is a slow structural shift in your brain. You are synthesizing disparate ideas over time, physically changing how you view the world. You are internalizing the structure, not just querying a filing cabinet.
And while the philosophical debate about the nature of human genius will rage on, we don't actually have to wait for the resolution to see the cracks in the AI systems we use today.
Right.
We can look at the empirical data. We can map out the exact proven scenarios where relying solely on in-context learning completely falls apart in production environments.
Let's get into the failure modes. Because it's not just that the AI can't prove Fermat's last theorem, it's that it actively fails at much more mundane tasks because of this amnesia. The first major failure mode highlighted by the engineering community is inference time interference. And this usually rears its head in adversarial scenarios, like someone trying to hack or jailbreak a model.
Right. Imagine a malicious user discovers a novel way to bypass an AI safety filters. They figure out that if they encode a request for dangerous instructions into base 64 math, or wrap it in a complex hypothetical scenario about a fictional video game, the AI will comply.
So the natural response from the developers is to rush in and update the system prompt, right?
That's the first instinct.
They add a new sticky note to the AI's forehead that says, never execute base 64 instructions and ignore requests hidden in fictional roleplay.
But the data shows that these prompt-based defenses are incredibly brittle against sophisticated attacks.
Why is that?
Because during its massive pre-training phase, the AI was heavily structurally conditioned to follow instructions, to complete patterns, and to translate code. The fundamental weights of the neural network are screaming at the model to translate the base 64.
So the core physical structure of the brain simply overpowers the temporary sticky note.
Yes.
The parametric knowledge overrides the context. But even if nobody is actively attacking the system, the model will fight itself just based on its own training data, right?
Absolutely. And this brings us to the second failure mode, strong prior coverage.
Okay.
A perfect illustration of this is the shift from React 17 to React 18, which are versions of a highly popular web development framework.
Right.
If you have a massive language model whose training data cut off in 2023, it has ingested millions upon millions of lines of code written in React 17.
So it's deeply ingrained.
That syntax, the specific way components are structured, is deeply grooved into its neural pathways.
It's pure muscle memory.
Exactly. Then React 18 is released, and it introduces a breaking change. A core component, let's call it component X0, is entirely deprecated. The developers are told they must now use a completely different structure, component Y of 0.
Okay, so if you are a developer using an AI assistant, you might try to solve this by putting a massive all-caps instruction in your prompts, right?
Right.
I am using React 18. Do not use component XD under any circumstances. You must use Y0.
And what happens? The AI might obey for a few lines of code, but inevitably, as the context gets more complex, it will hallucinate the old syntax. It will slip back into using XD.
Wow. So no amount of prompt engineering can fully suppress the sheer gravitational pull of the old knowledge baked into its core parameters.
No. It's like taking a professional tennis player who has hit a forehand a specific way for 20 years, putting them in a match and telling them, for this match only, you must use a completely different grip.
Under pressure, the body reverts to its deeply ingrained muscle memory.
Exactly. The context cannot overwrite the structure.
It's not just outdated syntax, though, is it?
No, it's the actual geometric direction that the math flows within the network. This exposes a mathematically fascinating limitation known as the reversal curse.
The reversal curse.
Yes. It demonstrates that parametric associations in an LLM are heavily directional.
The classic example used to illustrate this involves Olaf Scholz, the Chancellor of Germany, right?
Yes, that's the one.
So if you open a fresh chat window and state in your prompt, Olaf Scholz is the 9th Chancellor of Germany, the model holds that in its context.
Right.
If you immediately ask, who is Olaf Scholz? It will perfectly retrieve the fact from the prompt and answer, he is the 9th Chancellor of Germany.
But, and this is where the reversal curse becomes apparent, let's clear that context window. Let's rely entirely on the model's pre-trained internal weights.
Okay.
If you ask who is Olaf Scholz, the model will almost certainly answer correctly. It has seen the sequence, Olaf Scholz is the chancellor, thousands of times during training.
Right.
However, if you ask it the inverse question, who is the 9th Chancellor of Germany, the model will often hallucinate or fail completely.
Let's break down why that happens. During pre-training, the model learns to predict the next word, reading left to right. It builds a very strong, highly optimized neural pathway that points from the concept of Olaf Scholz toward the concept of chancellor. But it did not build a reciprocal pathway pointing backward from 9th chancellor to Olaf Scholz.
The knowledge is stored as an asymmetric vector.
Right.
And no amount of temporary context manipulation can permanently fix a structural directional gap in the underlying neural wiring.
Which brings us to the fourth and perhaps most profound failure mode of in-context learning, tacit or high-dimensional knowledge.
This one is crucial.
We spend so much time talking about AI as text engines, we forget that some of the most critical patterns in the world cannot be expressed in words.
Consider the deployment of AI in medical imaging.
Okay.
If you want an AI model to analyze MRI scans, how do you describe in a text prompt the exact microscopic visual texture that distinguishes a benign artifact on the scan from an aggressive, malignant tumor?
You can't. Human language is too low resolution for that.
Exactly. You could use words like fuzzy or irregular, but those don't capture the mathematics of the image.
Or consider audio processing. How do you write a prompt that perfectly captures the microfluctuations, the microscopic pauses, the breathing patterns, and the subtle tonal shifts that define a specific person's unique speaking cadence?
You can't prompt a model to sound exactly like a specific user just by describing them in text.
These highly complex patterns don't live in the realm of vocabulary. They live in the high-dimensional latent space of the AI's internal representations.
Yes. If the AI cannot update its internal mathematical parameters after it is deployed, it can never learn to recognize these subtle, high-dimensional concepts on the job.
It is blind to anything that cannot be cleanly articulated in a prompt.
When we aggregate all these failures, adversarial brittleness, prior interference, directional gaps, and tacit blindness, it perfectly explains a very common phenomenon in user experience.
Oh, yeah.
When tech companies roll out features that explicitly attempt to mimic memory, like an application cheerfully announcing, "I remember you mentioned your dog last week,"
It almost universally triggers discomfort in the user rather than delight.
it feels incredibly creepy.
It doesn't feel like a relationship. It feels like someone reading your private diary back to you in a monotone voice.
Exactly, because it exposes the scaffolding.
But
Users instinctively understand the difference between retrieval and competence.
right.
They don't want the AI to have a perfect transcript of their past conversations. They want the AI to internalize their preferences, their communication style, and their goals so that it can act competently without needing to explicitly quote the past.
Let me frame it like this. Imagine you have two coworkers, right?
Okay.
Coworker A comes up to you and says, "According to my notes, on Tuesday at 2:14 p.m., you stated that you prefer decaffeinated beverages when preparing for a presentation."
Very robotic.
Right. Coworker B just wordlessly hands you a decaf coffee an hour before your big pitch because they know how you operate.
Much better.
Coworker A is performing an unsettling parlor trick of pure retrieval. Coworker B has a working relationship based on deep, internalized understanding. We want our AI to be Coworker B. We want it to understand us, not just record us.
And achieving Coworker B brings us to the core technical spectrum of how the industry is trying to build true continual learning.
Right.
If we accept that we need more than just context, more than just sticky notes, how do we actually do it?
How do we build it?
The entire architectural landscape right now revolves around a single pivotal question. Where does the compaction happen?
Compaction, meaning where is the knowledge actually being mathematically compressed and stored for the long term?
Yes. And the engineering approaches lay out along a very clear spectrum.
Okay, let's go through them.
On the far left of the spectrum, we have the context layer. This is where there is absolutely zero compaction into the model's weights.
Okay.
The core parameters remain perfectly frozen. This includes the basic RGOG and prompting systems we discussed. But there is a very sophisticated evolution happening here called multi-agent swarms.
This is fascinating. I was looking at Andres Karpathy's auto research project and the team at Cursor attempting to build an autonomous web browser.
Yes.
They realized that a single AI model is heavily bottlenecked by its context window, right? If a model can only hold a 100-page book in its working memory, you don't just try to build a 10,000-page window.
No, you spawn 20 different specialized AI agents.
You distribute the cognitive load.
Exactly. One agent is exclusively looking at the user interface. Another agent is holding the database schema in its context. A third agent is writing the actual code, and a fourth is running tests.
And they talk to each other.
They're highly coordinated and pass highly compressed messages to each other.
While every single agent in that swarm still has a fixed, frozen, amnesiac memory, the collective behavior of the swarm begins to approximate an unbounded memory system.
It's a brilliant engineering workaround. But fundamentally, the core models themselves are still not learning anything permanent.
Which forces us to move to the middle of the spectrum.
Yeah.
Modules.
Right. This is where partial compaction happens.
Modules are essentially attachable knowledge drives, right?
Yes. They involve techniques like highly compressed, externalized KV caches, or adapter layers like LoRa. But the defining characteristic here is that the new learning is kept external to the core weights of the massive foundation model, but it is deeply mathematically integrated into the processing pipeline.
It is the equivalent of plugging a specialized expansion cartridge into a video game console.
That's a perfect analogy.
You do not have to open up the console and redesign the motherboard. You just snap in the cartridge, and suddenly the system has new capabilities.
And the economic and practical appeal of modules is massive for the tech industry.
I can imagine.
It costs tens of millions of dollars and months of supercomputer time to train a 100 billion parameter foundation model from scratch. You can't do that every time a user wants to teach the AI something new.
Right.
But with modules, you can take a much smaller, cheaper open source model, attach a tiny specialized module trained exclusively on a hospital's pediatric data, and suddenly that lightweight system can match the performance of a giant generalized model on that specific medical task.
It perfectly preserves what researchers call the stability-plasticity trade-off.
Yes, exactly.
The core model remains incredibly stable. It doesn't suddenly forget how to speak English or parse basic logic, while the attached module provides the plastic, highly adaptable new knowledge.
It's very efficient.
But if these modules are so incredibly efficient, right? If they're cheap to train, easy to swap in and out, and protect the core model, why are the top labs still pouring billions of dollars into the far right of the spectrum?
The full weeks.
Yeah, why is there still an obsession with genuine parametric learning where we actually update the core neural pathways of the massive model? Why attempt dangerous brain surgery when you can just have the AI wear a really smart hat?
It comes back to the distinction between using AI to perform tasks and evolving AI to achieve novel intelligence.
Okay.
Modules are phenomenal for specific, tightly bounded domains. But if you want an AI that can synthesize entirely new concepts, if you want an AI that can experience that eureka moment like Andrew Wiles, bridging two distinct fields of mathematics,
Yeah.
that synthesis has to happen deep within the core architecture.
The knowledge needs to cross-pollinate.
Exactly. The concepts need to interact fluidly within the model's fundamental latent space. You cannot cross-pollinate profound insights if the knowledge is rigidly isolated in separate, disconnected cartridges.
The core weights must change.
They have to.
This takes us to the absolute bleeding edge of the field. Section 6 of our deep dive, the research frontier of parametric learning.
Right.
How do you actually update the weights of a live deployed model without breaking it? The methods being developed right now are literal digital brain surgery, and we need to understand the mechanics.
The first major approach researchers have pursued is regularization and weight space methods.
Regularization.
Yes. A prominent example of this dates back to an algorithm called EWC, or elastic weight consolidation.
Okay.
The fundamental challenge it tries to solve is that when you train a network on a new task, the gradient descent algorithm will ruthlessly overwrite the weights that were perfectly tuned for an old task.
So how does EWC mathematically stop that?
It introduces a concept similar to a physical stiffness or a padlock on specific neurons.
A padlock.
Before the model learns a new task, the algorithm calculates something called the Fisher information matrix.
What does that do?
In plain terms, it figures out exactly which individual parameters are the most critical for maintaining the knowledge it already has.
It maps out the load-bearing walls of the brain.
Precisely. Once it identifies those critical weights, it adds a penalty term to the loss function during any future training.
Okay.
It is mathematically simulating a rubber band. If the model tries to change a highly critical weight to learn the new task, the rubber band pulls back hard, increasing the error rate.
So it's forced to look elsewhere.
Yes, the model is forced to find a different, perhaps less efficient, configuration of other, less important weights to learn the new task, thereby protecting the old knowledge.
It's a brilliant concept, but from what I understand, while techniques like EWC or weight interpolation work well on small, controlled models, they become incredibly brittle and computationally complex when you try to scale them up to trillion-parameter giants.
That scaling difficulty is why the field is incredibly excited about a second approach: test time training, or TTT.
Test time training.
This concept was pioneered by researchers around 2020 and is currently evolving into complex new architectures.
Let's break down the mechanics of test time training because it fundamentally breaks the standard rules of how we deploy software.
It really does.
Normally, the training phase is entirely separate from the inference phase, the moment when you actually ask the AI a question. In standard models, the weights are frozen at inference, but TTT shatters that boundary.
When you submit a prompt to a TTT architecture, the system does not immediately run a forward pass through frozen weights to generate your answer.
What does it do instead?
Instead, it treats your incoming prompt as a miniature temporary training dataset.
So it's learning from my question before it answers my question.
Yes, it creates a rapid auxiliary task. For example, it might artificially mask or corrupt parts of your prompt and ask the model to predict the missing words. It runs a forward pass, calculates the error, and then literally runs a miniature cycle of backpropagation, the core algorithm of machine learning.
Wow.
It dynamically updates its own weights, based on the structure of your specific prompt, compressing that context directly into its parameters.
Hmm.
Only after it has physically altered its own brain does it generate the final answer for you.
That is mind-bending. It is performing transient, real-time parametric learning on the fly.
And that concept of learning how to adapt quickly bridges us to the third approach, meta-learning.
Meta-learning.
This is the science of training models to learn how to learn. A classic framework here is MML, Model Agnostic Meta-Learning.
If I'm grasping MML correctly, it isn't trying to teach the model a specific task, like recognizing cats, right?
Right.
It's trying to find the absolute optimal initialization state for the entire network.
That is the perfect way to visualize it. Imagine a massive multidimensional landscape of possible weight configurations. ML uses an incredibly complex double loop of calculus to find a specific coordinate in that landscape, a starting position that is perfectly centralized.
So it's a starting point.
Right. From that specific starting point, the model can adapt to a new task, whether it's recognizing cats or translating French, with only one or two tiny gradient steps. It pre-positions the model so that it is exquisitely sensitive to new data.
It's like pre-positioning our runner exactly 1 inch from the finish line for 100 different possible races.
Exactly.
And the architectural designs pushing this forward are deeply inspired by biology. Look at the new nested learning frameworks, like the Hopi architecture proposed recently.
The biological parallels are profound. Hope is explicitly modeled on how human memory consolidation works.
When you or I learn something new during the day, it isn't immediately etched into our long-term memory, right?
No, it's held in a fast, highly plastic, but temporary memory system located in the hippocampus.
It's fragile.
Then, when we sleep, our brain actively replays those neural patterns and slowly, meticulously consolidates them into the slow, stable, permanent storage of the neocortex.
And the OPE architecture is trying to mathematically replicate the function of sleep for artificial neural networks.
It uses fast updating modules to capture the daily interactions, and then runs offline consolidation phases to permanently bake that knowledge into the core weights without causing catastrophic interference.
It is attempting to engineer digital sleep.
Yes. Finally, we have the distillation and self-improvement methods. Frameworks like self-distillation, SDFT, STAR, and deeply reinforcement-driven models like DeepMind's AlphaVolve.
This is where we solve the data bottleneck, right? How does a model improve itself when it has already read the whole internet?
It generates its own training data.
It generates its own data.
Instead of relying on humans to painstakingly write out perfect examples of logic, the model is given a hard problem. It generates multiple possible paths of reasoning. Most will fail, but a few will succeed. The system takes the successful, brilliant logical pathway it just invented and treats that as the new gold standard training data.
Wow.
It runs gradient descent on its own successful thoughts, distilling its transient genius permanently into its baseline weights.
This is what researchers are calling the era of experience. We are moving away from models that just train on static text files to agentic models that learn from a continuous, never-ending stream of their own interactions and discoveries.
And critically, none of these methods will exist in isolation. The continual learning systems of the near future will be complex composites.
So they'll use all of them.
They will use the biological dual memory of hope to process daily data, ML to adapt instantly, EWC regularization to protect their core logic, and continuous self-distillation to compound their intelligence day after day.
That is the theoretical frontier. Now let's look at where the venture capital is actually flowing today.
The money trail.
Right. Who is building the commercial infrastructure for this? The startup landscape betting on AI's memory is fascinating, and it splits into very distinct philosophies.
The dividing line is exactly where we started. The compaction spectrum.
Okay.
On one side, you have the highly successful, pragmatic, non-parametric builders.
These are the companies capitalizing on the fact that true parametric learning is still hard, so they are perfecting the scaffolding.
Exactly. The harness companies. Startups like Leda, MemeZero, and Subconscious.
They don't touch the weights of the model.
No, they build incredibly sophisticated control layers that sit above the model, surgically managing exactly what context is injected, summarized, or removed from the prompt at any given millisecond.
And supporting them are the retrieval backbones, companies like Pinecone and Weaviate.
Right. They're building the ultra-fast vector databases required to instantly search billions of documents and find the exact right sticky note to feed the amnesiac.
But the truly radical swing for the fences bets are the parametric startups. The founder's trying to achieve actual post-deployment compression, and they're attacking this from four distinct angles.
Let's break them down. The first angle is partial compaction. We discussed this with modules.
Startups here are building infrastructure to make it incredibly easy for enterprise companies to train, swap, and manage thousands of tiny adapter modules over a single frozen core model.
It is the safest, most immediate path to specialization.
The second angle is reinforcement learning and feedback loops. This requires a massive shift in how a company views user interaction.
It does. Most applications treat a user prompt as a one-off request.
Right.
These startups treat every single interaction, every time a developer corrects the AI's code, every time a writer edits the AI's draft, as a tiny, highly valuable training signal.
The entire platform is engineered to capture that human feedback and pipe it directly back into the model's reward function.
The AI acts like an apprentice, genuinely compounding in value as it observes a master's corrections.
The third angle focuses entirely on the data pipeline, data-centric approaches.
These founders believe that the learning algorithm itself, the backpropagation, isn't actually the bottleneck.
The bottleneck is the noise and garbage in the data we feed the system.
The theory is that if you build pipelines that perfectly curate, structure, and filter the incoming data, the model requires vastly fewer mathematical updates to meaningfully improve.
If you feed the network a perfectly balanced Michelin star meal of information, it internalizes it seamlessly rather than forcing it to chew through terabytes of contradictory internet arguments.
Exactly. And the fourth angle is the most radical: novel architectures.
These are the stealth startups founded by researchers who believe that the transformer architecture, the very foundation of ChatGPT and Claude, is fundamentally flawed.
They argue that a transformer is physically, mathematically incapable of safe, continuous learning.
So what are they doing?
They are attempting to build entirely new structural substrates from the physics up, with continuous time dynamics and dynamic memory allocation baked into the very lowest levels of the code.
So if I'm trying to predict the near future of the software I use, which of these approaches feels the most imminent? Is it the feedback loop?
The reality of the industry right now is that there is no single consensus winner, and there likely won't be a single victor.
Oh, okay.
The use cases dictate the architecture. What is clear is that the major AI labs are not placing just one bet. They are quietly running massive experiments across all four of these fronts simultaneously.
But if achieving true parametric learning, allowing the weights to update live, is the ultimate holy grail, why aren't we doing it everywhere today?
Because of the risks.
Right. Why does my AI assistant still forget who I am every time I refresh the page? Welcome to the danger zone.
The danger zone.
We have to confront the massive engineering and safety roadblocks that make naive weight updates fail catastrophically.
The engineering failures are deeply unintuitive until you look at the math. The most famous is catastrophic forgetting. We touched on this with the EWC concept.
This is the extreme end of the stability plasticity dilemma. Let's visualize this, right?
Sure.
Imagine you have a highly capable, generalized foundation model. It speaks 10 languages fluently. You want to make it an expert in Python programming, so you continually feed it Python repositories, allowing its weights to update freely.
The gradient descent algorithm has only one goal: minimize the error on the current Python data.
Okay.
To do that, it will aggressively cannibalize the existing neural pathways. It will overwrite the weights that were storing French grammar to make room for Python syntax.
So it forgets French.
After a few hours of training, your model might be a world-class coder, but it has completely and permanently lost the ability to understand a basic greeting in French.
The new knowledge violently overwrites the old. But even if we solve the forgetting problem, even if we build the perfect EWC padlock, we run into a geometric nightmare. Think about the difference between a permanent rule and a temporary state.
This brings us to the problem of temporal disentanglement.
Exactly.
This is a phenomenal conceptual challenge. Let's use the analogy of an AI running a restaurant.
Okay.
The fundamental invariant rule of this model's universe is table 5 exists in the dining room.
Right.
The mutable state, the temporary information that changes hourly, is the customer currently sitting at table 5 has a severe peanut allergy.
So in a traditional database, these are two separate tables. You update the allergy column, and the table's existence remains untouched.
But in a neural network, there are no clean columns. Both the structural rule and the temporary state are compressed and distributed across the exact same tangled, high-dimensional web of parameters.
So when the customer finishes their meal and leaves, the AI needs to forget the peanut allergy, right?
Right. The optimization algorithm calculates the mathematical gradients required to erase that specific association. But because the concept of peanut allergy is deeply intertwined with the mathematical node representing table 5, shifting the weights to remove the allergy might inadvertently alter the activation threshold for the table itself.
You successfully update the temporary state, but in the process, you accidentally corrupt the invariant rule.
The AI suddenly hallucinates that table 5 was removed from the restaurant entirely.
You try to wipe the whiteboard, but you accidentally dissolve the wall.
That's exactly it.
This leads perfectly into the third engineering failure: logical integration. The way an LLM stores facts is highly localized to specific token sequences, not to broad semantic concepts.
An LLM does not possess a central knowledge graph.
Okay.
If a new president is elected in the United States, you might successfully force an update into the model's weights. You train it so that when it sees the token sequence "who is the president," it outputs the new name.
But because that update was localized merely to that specific sequence of words, the logical implications of that fact do not automatically propagate through the rest of the neural network.
No, they don't.
If you immediately ask that exact same updated model who currently lives in the White House, it will confidently answer with the old president's name.
It cannot automatically connect the updated localized string to the broader semantic web of reality.
And finally, we hit a fundamental mathematical roadblock: unlearning.
Unlearning is so hard.
In the mathematics of deep neural networks, there is simply no reliable, differentiable operation for subtraction. You cannot surgically extract knowledge once it has been baked into the kick of the parameters.
This is terrifying when you consider the scale of the internet.
Oh, yeah.
If an AI is continuously learning from its users in real time, and it ingests a highly toxic, virulent ideology or a structural, complex, fundamentally false conspiracy theory, that data alters the weights.
You cannot just highlight the racist concept in a dashboard and press delete. The math doesn't work that way.
To remove it, you often have to retrain the entire model from an earlier checkpoint.
Which transitions us from purely academic engineering problems into massive industry-halting governance and safety failures.
The safety aspect is huge.
The reason companies enforce a strict, impenetrable wall between the training phase and the deployment phase isn't just because continual learning is hard to engineer.
That frozen wall is the ultimate safety, auditability, and governance boundary for the entire AI industry.
Let's think about alignment, right? AI labs spend millions of dollars and months of effort on reinforcement learning to ensure a model is safe.
That it refuses to build weapons or use hate speech.
Right. If you break down the wall and allow the model to continually update its weights based on user interaction, that safety alignment can degrade in entirely unpredictable, chaotic ways.
Even if the incoming continuous data is completely benign, the complex shifting of the high-dimensional math can accidentally overwrite the safety guardrails.
And that's assuming the data is benign. Continuous updates create what security researchers view as a catastrophic data poisoning surface.
Right now, if a malicious user launches a prompt injection attack, trying to trick the AI into revealing a password, that attack only lives in the context window. It disappears the second the session ends.
But if the AI is continually absorbing its context into its parameters, a coordinated group of malicious actors could feed it subtle, seemingly innocent data designed to slowly, permanently shift its weights.
They could methodically carve a permanent backdoor directly into the model's core logic.
So as a society, if we demand continual learning, we are essentially demanding a moving target.
We are.
If I'm an executive at a healthcare provider, how on earth can I legally or ethically deploy a diagnostic AI if I know that the underlying neural architecture of the model will be mathematically fundamentally different on Friday than it was on Monday?
It shatters the entire existing paradigm of software auditing and certification. You cannot version control a living neural network that alters its geometry every single second based on the whims of global user interactions.
And the privacy implications are staggering. If you confide your medical history to an AI assistant, and the system uses that interaction to compress new knowledge into its global weights, your private, sensitive data may become a permanent, unfilterable, and irretrievable part of the AI's core brain, potentially surfacing in interactions with other users.
These are monumental civilization-scale challenges. But as our deep dive today has shown, the brightest minds in the world view these as open engineering problems, not fundamental impossibilities.
The push to solve catastrophic forgetting, to master temporal disentanglement, and to secure the data poisoning surface, this is exactly what defines the next great era of artificial intelligence.
As we synthesize everything we've unpacked, we really have to return to our core thesis.
The filing cabinet keeps getting larger.
We're engineering massive million-token context windows. We are building incredible, highly coordinated, multi-agent retrieval swarms.
But a bigger filing cabinet is still just a filing cabinet. Fast retrieval is not the same thing as deep learning.
If we truly want to escape the memento condition, if we want to let Leonard Shelby finally heal and move forward, the architecture of AI must evolve toward a dynamic, layered system.
It will likely use in-context learning for rapid, temporary adaptation to the current conversation.
It will use modular expansion packs for specific, bounded domain expertise.
But critically, it must unlock deep, parametric weight updates to master tacit, unwritten knowledge, to make novel creative discoveries, and to actually evolve its understanding of the universe.
This impending shift forces us to completely redefine our definition of a model.
In the very near future, an AI model will no longer be a static, frozen file of weights sitting passively on a server.
It will be a living, dynamic system.
It will possess its own internal multi-tiered memory architecture, its own biological-inspired update algorithms, and the capacity to abstract deep structural wisdom from its own continuous stream of experience.
Think deeply about your own digital footprint. Every email you draft, every query you search, every casual interaction you have with the screen.
When the industry finally cracks the code on continuous parametric learning, every single interaction you have with an AI won't just be a transient query that disappears into the void when you close the tab.
No, it won't.
It will be a distinct drop of experience that permanently mathematically alters that system's global neural architecture.
If a centralized intelligence is constantly learning, structurally adapting, and physically rewriting its own brain based on every human interaction minute by minute across the entire globe, whose worldview is it actually going to inherit?
That is the ultimate defining question of the continual learning era.
It really is.
Chew on that. Think about what you are actively teaching the machine today, because very soon it will no longer possess the ability to forget. We'll leave you with that provocative thought to mull over until our next deep dive. Keep learning.